Okay, we've seen what would be the effect of revolution time to speech intelligibility in a room or in a hall. So we need to tune it to a specific value so that we can hear speech properly, or we can catch what the others are talking in that particular room. Okay. Um, it is related specifically to the size of the room, the volume of the room, as well as the amount of absorption in that particular room. So our revolution time, I can call it as RT or T60 revolution time for it to reduce 60 decibel. Um, it is related to volume. Okay, so we have direct correlation with volume. Oops. And also the total amount of absorption in a particular room or hall or area or space. Okay, and from empirical data, uh, there is a Sabina equation being developed for that. Okay, based on Sabina, of course, and it is equal to 0.161 times the total volume divided by the total room absorption. Okay, so A here is also equals to the average absorption times the total surface area, total exposed surface area in that particular room. Okay, so this is our total absorption, right? And this equation is valid only if we assume that we have a diffuse field, okay, and the absorption for all material inside this area is less than 0.2. Basically, there are some reflection as well. Okay, it's fairly live region, or more than average, I would say. Okay, to live region. So we are talking about the area being covered here, from average up to live uh, space area, or area with reflection. Okay, we are not talking with area that absorb lots of sound energy. Okay, so this is where Sabina equation can be used. All right. If we have different types of acoustic environment, okay, for example, if we say, okay, average absorption coefficient is now uh, larger than 0.2, and we have uniform distribution of absorption, then A might not be uh, summation of alpha times the surface area. Now it's become alpha. Okay, so it's a different equation already. And we have if we have a non uniform distribution with alpha I uh, larger than 0.2 for at least one material inside that particular room, so we are using Millington-Setter equation. Okay, and if we are saying that the room absorption is not constant, um, in this case we are uh, using A plus for MV. Okay, whereby we have uh, the effect of temperature and humidity inside the particular area. Okay, but for our case, we are limiting ourselves to just using the Sabine equation only. Okay, but it's just to let you know that um, this equation might not apply to all the cases available. Alright, so this is example of the effect of humidity and uh, frequency as well as temperature to our room constant. Okay, to the absorption inside a particular uh, area or in the air. Okay, so the energy of attenuation will depends on uh, humidity, temperature, as well as frequency. Okay, so everything is interrelated. Okay, but for our case, we just use Sabine equation for most of the typical cases. All right, so this is example of how we use Sabine equation. Let's say we have a space, a factorial space, whatever space it can be, and we were given the dimension of this space in terms of height, width, and length. And then based on this height, width, and length dimension, we can calculate what will be the total surface area of this particular room, and also the total volume of this room or space. Okay, and from these two, total exposed surface area and also the room volume, we can calculate what will be the revolution time using Sabin equation. Okay, so this is our Sabin equation here. So we have 0.161 times room volume over the total absorption, basically total space area times the average absorption coefficient, alpha bar here. All right. In this case, we are using different terms. Instead of saying fairly live, we are saying it is fairly hard. Basically, it reflects sound. Okay, so it means the same thing. So based on this Sabin equation, we can calculate what will be the revolution time for this particular area, which is 4 seconds. All right. And we can also calculate what will be the room constant, which is equals to total absorption divided by 1 minus absorption, average absorption for this area. Okay, so we have room constant equals to 284 meter squared. Okay, so this is how we use the equation for solving this problem. All right. We can also furnish the area with some seats. For example, in this case, we're assuming that we have seat with absorption equals to 0.5 meter squared. Okay, and we want to know what will be the quantity of seat that is needed in a hall with volume of 2000 meter squared if we want to control the revolution time as RT equals to 1 second. Okay, we want RT equals to 1 second. So based on Sabin equation, we know revolution time T or T 60 second. Sometimes I just wrote T here or T 60 second or RT. They are the same basically. Okay, so from this we can rearrange to get absorption equals to 0.161 times V over T. Okay, so to have 1 second revolution time, A will be equals to 0.161 times the volume 2000 over 1 second. Okay, so this is the amount of absorption. So if we're told that each seat is giving us 0.5 meter squared absorption, so the maximum number of seat will be equals to 322 divided by 0.5, so we have 644 seat. Okay, so this is the maximum number of seat. If we put more seat, what will happen? It will absorb more sound, so our revolution time will be much less. If we put less seat, so our revolution time will be much higher than 1 second. Okay, so if we want to know what will be the volume per seat, for example, we can just take 2000 meter squared divided by 644, so we have 3.11 meter cube as the volume per seat. Okay, so obviously the volume being covered by one seat. Alright. Normally, if we have a hall and we want to do revolution time measurement, we will excite a noise, a white noise. Okay, and then we start our measurement, and then when the noise subside, okay, we can see the trend of the measured sound pressure level. We will be measuring or capturing the time it takes for the sound to reduce by 60 dB. Okay, so this is one example of revolution time measurement done in a hall. Of course, we will not be doing the measurement at one location. Okay, we will do the measurement at multiple location, and we will repeat the measurement so that we will get an average value, okay, for a particular space.
Reverberation time measurement. Press the start key at least 1 second before the noise source starts. The unit goes into trigger standby mode. The measurement data is stored starting from 1 second earlier than when the trigger level is exceeded. The measurement store address is shown on the right.
Okay, so basically you can see from the measurement, initially they are playing white noise through the hall speaker, or if they don't have any speaker, we will introduce a sound source that will create this white noise, and then it depends on the amount of absorption and also the volume of the hall. We will reach to a certain sound pressure level. Okay, for example, in this case, this will be the maximum for that particular hall, 85.6, and then we start our measurement and we suddenly stop the sound source. When we stop the sound source, it will decay. Okay, the sound energy will decay due to the amount of absorption in that particular hall. Okay, it will decay, but it will not fall to zero. Okay, it will fall to a background noise level within that particular um, hall. Okay, which is equals to 47.3. So from 80 to 47.3 is roughly about 30 to 40 dB. Okay, so we are not reaching 60 dB at all. So as what I've mentioned earlier, we will interpolate, or basically the um, device itself will do the interpolation for you. Okay, so we will do exactly the same thing at different location. Okay, so based on multiple measurement, we will average out what will be the. So that's the idea how we do revision time measurement. In fact, you can do this by your own. Okay, nowadays even using smartphone, right? You can uh, set up your app, revision time measurement app, using your smartphone, and you can clap in that particular room. Okay, so you clap. Doing so will introduce a high sound pressure level in that particular room. So once your clap finish, the sound source is gone. Suddenly the sound pressure level drops, and the rate of the sound pressure level drops will depends on the amount of absorption in that particular room. You can do this for a small room, it's acceptable, but if you have a large hall, probably your small clap will not introduce high enough sound pressure level. Okay, so the interpolation might not be accurate enough, okay, to get the revision time. All right. In a hall area, normally revision time measurement can be done. We also spec the room, okay, according to noise rating. Okay, it's based on ISO standard. So certain application will have certain noise rating. Okay, the lower the noise rating, the better in terms of absorption the room needs to have. Okay, the lower the noise rating, that means the room can be exposed to high level of noise, basically. Okay. So construction work, for example, certain area probably require certain room or hall to have this kind of noise rating. Okay, so for each noise rating, you'll see that the permissible sound pressure level or the maximum sound pressure level is changing with respect to frequency. Okay, so each octave will have its own maximum sound pressure level. Of course, the value is much higher at lower frequency compared to higher frequency. Why is that? Because this noise rating value is actually reflecting our sensitivity to noise. Okay, we are more sensitive to high sound pressure level at high frequency compared to high sound pressure level at low frequency. So that's the reason why maximum sound pressure level is higher at low frequency compared to high frequency. Okay, if we take those value and put it in terms of graph, this is how we see it. Okay, so we are seeing that at low frequency we have higher tolerance to noise compared to high frequency. Okay, so let's say if you do measurement at different octave center frequency, and you get something like this. Okay, so you have different value at different frequency, and if you want to report what would be the NR value for that particular room, okay, you'll check it against these NR curves. Okay, so based on value here, we are saying that this is 0, then you have 10, 20, 30, 40, this is NR 50 line, and here is NR 60 line. So you can see that at some frequency, sound pressure level is higher than NR 50 line, but all of them are lower than NR 60 line. So we can say that this room meet NR60 requirement, okay, for all tested frequency. Okay, of course, uh, this NR value sometimes is misleading. Okay, some material is rated with certain NR value. You should know that the performance itself is frequency dependent. Okay, although, for example, in this case, we are saying, okay, the material is NR60 certified, we should know that the performance is uh, quite bad at these two frequency line or frequency region. Okay, it's good at the rest of the frequency, but not at these two frequency. So when comparing between material with the same NR rating, we should also check the actual performance based on frequency, because our problem might lies at this particular frequency. Okay, so we can have other material, for example, having some properties might be something like this. Okay, also meeting NR60 requirement, but in this case the material is having problem at this region, okay, at low frequency region, and somehow our problematic frequency is at low frequency region. If we choose this material, then we are having problem, okay, later on, because the performance is not good at this frequency range. Okay, instead of absorbing the sound, we can also diffuse the sound. Okay, so we know straight away if we have a reflector, basically we will be reflecting almost same amount of sound energy if there's no absorption at all. Okay, if we have absorption, the sound pressure level will be reduced or attenuate depending on the amount of absorption that we have. Okay, but again, in both cases, absorption or reflection, the direction will be changed, okay, from the initial incident wave. Okay, so the incident wave might be coming along this side, so based on Snell law and so on, so we have our reflected wave. Okay, the same goes here, so we have our incident and then we have our reflected wave. Okay, so we have a specific incident and reflected wave direction. However, if we have a diffuser, what would a diffuser do? It will not change much in terms of the sound pressure level, amplitude, but it will change a lot in terms of the distribution of sound energy. Okay, where the sound will be reflected. Okay, so you can have the sound incident in one particular direction, and suddenly the sound energy will be directed towards all possible direction. Okay, when it is being reflected by the surface or by this diffuser. Okay, so this is another example here. If we have a flat reflector, so we have specific incident angle and specific reflected angle. If we have a reflection from a jagged surface like this, okay, so we will be seeing that it depends on the direction of the surface. The sound will not be directed, not be reflected along one specific direction, but it will depends on the surface. Okay, some is along one direction, the other are along different direction, and so on. However, if we control the surface itself, for example, by using quadratic diffuser and so on, we actually calculate the direction of the reflected sound. We can achieve something like this, almost a constant distribution of sound energy with respect to direction. Okay, so in extreme cases, you might be seeing something like this in a studio. You have a wood stick being arranged like this, okay, in different height. So the purpose of this wood stick is to reflect sound at different reflected angle, so it will diffuse the sound. Okay, so that's the idea of this extreme wall arrangement. So what's the effect of this diffusion. So this animation can illustrate that effect to you clearly. Okay, on the left hand side we have a room without any diffusion treatment. So let's say S represent our sound source. So the sound is coming from this point. Okay, so we can see that we have, let's say, drag this. All right, so this line okay, right, the line represent the area whereby the sound pressure level highest, okay, towards the wall, and then being reflected by the wall, assuming there's no absorption here. Okay, so it will be reflected again within this space. Okay, and we will be seeing that at certain area we have high sound pressure level, at certain area we have low sound pressure level. So it depends on where you are at which instant in time. So you can have high reflection or high sound pressure level or high sound, and then suddenly you have a quiet area in this particular room. Okay, so the sound energy is not constant. It's constant in this room, but the distribution is not equal at each area within this room. So with diffuser, okay, in this case we have diffuser here, line along the wall of the room. Again, the sound source is coming from the red dot. Now we are seeing that the diffuser is reflecting the sound in almost random direction, and in the end we will be having a diffuse sound pressure level. Basically, at any area within this room, we will have the same sound pressure level. Okay, almost the same sound pressure level anywhere. So that's the purpose of sound diffuser. All right. So in cinema, for example, we want the cinema to be treated with diffuser because we don't want the volume to be high at certain seat and low at certain seat. Okay, we want at every corner within the room, the volume or the sound should be almost similar. All right. Now let's take a look into absorption and insulation. Okay. So what is absorption and insulation? In layman's term, absorption means you want to absorb sound. Insulation means you want to block sound or stop sound. Okay, so to absorb sound, basically you want to absorb the acoustic energy within the sound, and to do this we want the sound to pass through the material. So the material needs to be a porous material, okay, because it needs to absorb the sound. In the case of insulation, we want to block the sound, so the material needs to be impervious, so it should not be allowing any sound to pass through it. Okay, normally we need a heavy mass material to do this. Okay, so absorption is to absorb sound energy, insulation is to block the sound energy. Okay, so if we have a good insulating material which is good to block sound, normally it's poor in terms of absorbing the sound. Okay, and the other way around is true as well. If you have some material that is good for absorbing the sound, it's not good for stopping the sound, okay, or insulating the sound. So we need to know for sound treatment which one we need to use in particular instances. For example, do we need to absorb the sound, or do we need to insulate the sound, or in a day if you can't do anything, do we need to isolate the sound? Okay, so to relate with something that you know, okay, for example, if you have water, if you want to absorb the water, we can use sponges that has a lot of porosity in it, so it's good for absorbing the sound, absorbing water. Okay, but you cannot hold water with sponge. Okay, so the water will pass through the sponge. Okay, if you have something that's impervious, for example, plastic container, it's not good to absorb water with plastic container, but you can hold the water with plastic container. Okay. In terms of absorption mechanism, typically we have three types that are most commonly used. The first one is using porous material, sponge, and so on. And then we can also use resonators in the form of panel or plates, as well as a volume resonator or in the form of cavity. Okay, so if we look at the performance with respect to frequency, normally porous material tends to be broadband in terms of effectiveness, but the effectiveness are limited to high frequency range most of the time. Okay, it depends on arrangement as well. For panel resonator, the effectiveness can be arranged in such a way that it is um, highest at certain frequency range, and it can be a bit broadband as well. Okay, however, for volume resonator or cavity resonator, normally it's a tuned resonator. Okay, it's effective only at certain frequency range. Okay, and it is not effective at all at other frequency range. So the easiest example for porous material would be sponge or foam. It can be also in the form of fiberglass, rock wool, okay, felt, carpet, fabric, curtain, okay, or even seat. Okay, so these are materials that is porous to the sound. Okay, so when the sound goes into this material, there will be a friction between the air motion and the material itself. So this friction will dissipate energy in the form of heat. Okay, so we can use porous material in so many common problems. For example, to reduce sound reflection coming from room modes, standing waves, echoes, and also speaker boundary interference problem. The effectiveness of this material depends largely on the thickness of the material and also the sound wavelength that is being in this material. And just like what I mentioned earlier, the absorption range is normally broadband in terms of frequency. Okay. However, where they are not effective at low frequency range unless we make it super thick or we have some air gap from the material to the wall. Okay, so these are the two things that we need to do to increase the effectiveness of porous material against low frequency sound. Alright, so this is an example of the performance of the absorption coefficient of felt against frequency as well as thickness. Okay, so we can see that we have one here corresponds to the thinnest felt, about 1 inch felt, and then it goes on to 6 inch felt. Okay, so we can see that all of them converge to a very good absorption coefficient. One means very good absorption, absorb almost all sound. Okay, so around this range, okay, basically we can say above 2000 hertz, thickness from 1 to 6 inch will absorb sound, okay, very well. However, lower than 2000 hertz, we are seeing that okay, the thicker the felt, the better the performance. Right. So for example, with 6 inch felt, you can have the same performance up to from 500 hertz and above. Okay, however, if you want a better performance below 500 hertz, you need a thicker felt to do that. Okay, so the thicker the felt, the better the performance will be in low frequency range. Okay, so as a rule of thumb, the lowest frequency that you can absorb using a porous material should have a wavelength of 4 times the material thickness, okay, or the absorbent thickness. So if we have 6-inch felt, the lowest sound frequency that can be absorbed will be equals to uh, a frequency with wavelength of 4 times 624. Okay, that's how we uh, uh, find the thickness of suitable porous material for absorbing sound at certain frequency range. Okay, so if we relate back what we have learned so far about the physics of sound, this is our wavelength lambda. It's related to speed of sound c in air over frequency. So if frequency goes higher, lambda goes lower, but if frequency goes lower, lambda goes higher, since we have a c that is almost constant, right? So in this case, for example, at 1 kilohertz, our wavelength is 1 feet or about 30 centimeter. Okay, so that means to absorb sound at 1 kilohertz, we need 30 divided by 4 centimeter. Okay, about close to 10 centimeter thickness of felt or foam to absorb the sound. Okay, so you can imagine what happens if we go lower. For example, in the worst case scenario, at 20 hertz, the wavelength is 17 meter. Okay, so 17 meter wavelength. To stop sound with this frequency, you need 1/4 of the thickness. Okay, basically almost 4 meter width of or 4 meter length of foam is needed to absorb the sound properly at this frequency. So that's the reason why most of the time when we use porous material, we are absorbing sound mostly at high frequency range and not at low frequency range. Okay, for low frequency range, we need different strategy. Okay, absorption might not be the right strategy. Okay, so if we put the absorption material at certain distance from the wall, okay, we can also increase its effectiveness based on our understanding that the energy will be reduced mostly when we are absorbing at the location whereby the velocity is the highest. Okay, so that point happens to be a quarter wavelength from the wall. Okay, so as a rule of thumb, our air gap also needs to be quarter wavelength as well. Okay, so not only we can use a thick porous material, we can also put this porous material at certain distance from the wall. All right, but although I'm saying that it is mostly useful for high frequency but not effective at low frequency, you can find this porous material being used a lot since it is cheap and easy to construct compared to other types of absorbent material or absorbent approach. Okay, we can also use a resonant absorber. Okay, basically the idea here is you want the sound to enter this absorber and then resonate. When the sound resonate, it will vibrate at highest energy and of course lost most of its energy when it's vibrate. So that's how we reduce or absorb the sound. In terms of panel resonator, the idea is almost the same. Instead of having the sound within the resonator, now the sound is causing this panel plate to vibrate. Okay, the more the plate is vibrating, the more sound energy will be absorbed. Okay, so this flexible panel will vibrate in response to the incident sound. Right, so it depends on the flexibility of this panel. The more flexible it is, the better the performance of this panel, especially in terms of low frequency vibration. So the example of this panel can be in form of drywall, plasterboard, wallboard, gypsum panel, sheet metal, metal deck, and so on. Okay, normally these are the kind of material that people are using to construct rooms and so on. Okay, so you can have something like this. At the front here you have your panel, okay, and here you have your concrete wall. So we know concrete wall will not be absorbing sound, okay, it is insulating sound basically. So we have the panel that can absorb sound, okay, a certain degree. It can vibrate. To increase the effectiveness of this panel, we can also introduce an absorbing material in between the panel and wall, okay, and this material will have certain air gap, so we can tune the amount of sound being absorbed at certain particular frequency based on the cavity thickness, the thickness of the absorption material, the type of material, density of this foam, and also the hole within this panel as well. Okay, so for example, in this case, if you have a panel with certain mass density per area, so we have the natural frequency of this panel absorber will be equals to 60 divided by square root of m panel mass times cavity thickness T. Okay, so this another example of resonator, but instead of having plate resonator or panel resonator, now we have a volume resonator. Okay, so the most famous volume resonator will be Helmholtz resonator. Okay, so the equation is very simple for Helmholtz resonator. Basically, you have a volume, you have an opening for this resonator, let's say A, and then you have a neck for this resonator. All right, so the frequency of this resonator is equal to C over 2 pi times square root of A over the volume times the length of this neck. Okay, so when I say frequency, that means this resonator is good to absorb sound only at this particular resonator frequency. So the sensitivity of the resonator is highest here. Okay, at other frequency range, it will not absorb sound at all. Right. So let's see this demonstration. Now we have sound being played. So you can see at certain frequency, this resonator start to work. At certain frequency, this resonator starts to work. Okay, so what happened here, we have a speaker playing some tone sound. We have two cavity here, okay, two volume here with neck and also area, opening area. So looking at the neck length, both of them are the same. The opening area are also the same. The volume are different. So based on this equation, one is bigger than the other. So one Helmholtz resonator is effective at lower frequency compared to the other. So that's the reason why when I play this animation, the resonator on the left hand side starts to get excited first at certain frequency. Okay, before we reach that frequency, nothing happens to the sound. Okay, when we reach that frequency for the resonator on the left hand side, it starts to vibrate a lot. Basically, it absorbs the sound energy a lot there. And then when we increase the frequency further, now we are seeing that the resonator on the right hand side starts to vibrate a lot. And after some time, now we are seeing that the largest cavity, which is this guy here, is now behaving like a resonator. Okay. Alright, so that is our Helmholtz resonator. Basically, we are using this a lot, but probably you will not notice that. in action. Okay, one of them will be in your car. Okay, uh, to reduce the intake noise, which is very high. Okay, if we don't have this kind of specific frequency from our intake sound, right? In this case, since we have probably two problematic frequency, so we have two Helmholtz resonator with different volume and probably different neck as well. Okay, so these two are Helmholtz resonator in our intake. Intake. In the case of panel, sometimes you might see something like this in a hall, okay, whereby you have plates with holes, and the holes are designed in such a way that the opening are different. Okay, so what happens here, so each opening will have different cross-sectional area. The neck might be the same, but since the cross-sectional area is different, with the same neck and volume, will have different resonator absorbing the sound or tuned to the sound at different frequency. Okay, so this is another example of Helmholtz resonator disguised as a wall. We can also use the same concept to reduce the problematic area in the room. For example, we know that we have lots of reflection at the corner and so on, so we can install what we call as base trap closet. So the idea is still the same. So you have the porous material, so the sound will goes here and it will be trapped by this volume resonator. Okay, we can go even further using the idea. Instead of using normal brick, we can also use this kind of fancy brick with some cavity inside. So here we have our opening, so we have A here, and then we have our length of the neck, and then we have the cavity. So this opening is tuned to certain frequency, and to increase the performance of this Helmholtz resonator in the shape of concrete block, we can also put some absorption material here to increase the frequency along much wider frequency range. Alright, so we also have certain standard to classify the absorption within a material. Okay, so we have absorption value from 0 to 1. From 0.9 to 1, this is having absorption class of A. Basically, it's very good in terms of absorbing sound, and the lower the absorption coefficient, the lower the rating will go. Okay, so A will have the best ability and E will have the weakest ability. Of course, the absorption coefficient will not be constant with respect to frequency. Okay, it vary in terms of frequency as well. Okay, so you have to look at the performance of the material according to frequency when selecting the material. Okay, don't trust the rating, as simple as it is. Okay, to measure absorption, okay, experimentally in the lab, we have two approach to do that. The first one is to use revolution chamber. The other one is to use balance tube. So in the case of revolution chamber, we're assuming that the sound is coming at different direction, or basically in random direction or random incident. So the value that we are measuring will be the random incident coefficient of this absorption coefficient. However, if we use balance tube, we know that the sound is coming normal or 90 degrees with respect to the surface. So this absorption coefficient tends to be a normal incident coefficient. And normally, material are rated using impedance tube. Okay, testing using diffusion chamber tends to be more difficult, although it represents the actual condition much better compared to impedance tube. Okay, when we use revolution chamber, so basically we are calculating the absorption coefficient through its relationship with revolution time. Okay, so we put the material inside this revolution chamber, and we know this material will absorb sound. So we will measure what will be the revolution time with and without this material. Okay, and based on these two conditions, we will relate what will be the absorption value coming from the material itself. Okay, so we can calculate A using revolution time, and we do this in the revolution room, and we should make sure that the lowest frequency that we want our material to be tested at should adhere to this equation. Okay, so we want the room volume to have a specific volume. We want the room to have a specific volume so that we can achieve this minimum frequency. Okay, so every volume of room will have its own lowest frequency, so the frequency cannot go lower than this. Alright, so if we have 4 by 4 by 4 room, so the absorption coefficient can be measured only the minimum value can go down to 209.6 Hertz only. Okay, we cannot measure something lower than that. Okay, so we do the measurement without the material and with the material. So without the material, we will have one value of revolution time. With the material, we have another value of revolution time. But in this case, we know that the total absorption will include the absorption coming from the material itself. Okay, so the absorption coming from material will be equal to the surface area of that material exposed to the sound, as well as times the absorption coefficient for that particular material. So knowing these two rearranged, okay, we will have our absorption coefficient for that particular material given by this equation. Okay, so T160 is basically revolution time with the material. T060 is the revolution time without that material. Okay, so we can use this if we ensure that the material is not covering certain portion of the revolution chamber. Okay, if it is covering the floor or the wall of this revolution chamber, then the total absorption of the revolution chamber will also change. So the way to ensure that it will not affect the surface area of the revolution chamber is to hang the material. For example, we can hang the material using a cable or rope, okay, within that particular rope. Okay, that can be done. If we just put the material on top of the floor, for example, then we know that the absorption of the revolution chamber will change, or the total surface area will change. So that means that we have to do some minor modification to the equation. So that means we have to use this modified equation instead, okay, to find our absorption coefficient for that particular material. Okay, so this example, let's say we have empty classroom with this dimension, 10 meter times 8 meter times 4 meter, and the revolution time is 0.8 second. We were told that we have 50 tables with this dimension, okay, this surface area placed in the room, and the revolution time is 0.75. We need to calculate what will be the coefficient of this table if the surface area of this table is not covering the room surface, or if the surface area is covering the room surface for question B. Okay, so in this case, we need to use A for this equation, okay, and for B we need to use this equation. Alright, so we can calculate what will be the room volume, room surface area, and the absorption material surface. since we have 50 table, so 50 times the area of that particular table, so we have 35 meters squared. Okay, so we know T60 without the material and T60 with the material. So if we assume that the material or the table is not covering the surface of the room, the absorption coefficient will be using this equation, so we have 0.172. If the material is covering the room, so what we need to do, we need to find the average absorption coefficient for that particular room first. Okay, so that will be equals to 0.161 times the room volume divided by 0.8. okay, 0.8 without the material times the room surface area. So this is the average coefficient of the surface area for the room without the material. Okay, so the absorption coefficient for the material will be equal to 0.161 times the volume of the room divided by the absorption material surface or the table surface times 1 over T 160 minus T060 plus this guy here is our average absorption coefficient, okay, for that particular room. So basically it's actually this guy here, right? We just rearrange the equation. Okay, so this is another example. We have a room with this dimension at 1 kilohertz octave band, or this particular frequency. We were told that RT is equal to 1.4 second. If we then cover the floor with carpet, what will be the revolution time? And the revolution time was reduced to 1 second. What will be the absorption coefficient of the carpet? Okay, so basically in this case, we know the carpet is covering the floor. We need to use this equation. Okay, now the revolution, the absorption of the room is being affected by the presence of the carpet, so we need to use this equation. So again, we calculate what will be the room volume, room surface area, the carpet area, and the revolution time of the room without the carpet is 1.4. With the carpet is now equals to 1 second. That means we have to calculate what will be the absorption coefficient of the room without the carpet. So we have 0.119. So the absorption coefficient of the carpet now equals to 0.257, basically using this equation. This is another example, slightly different. I think you can read this by yourself. Basically, this topic and also topic for DB arithmetic are favorites for your final exam in terms of calculation, of course. Okay, because I can ask lots of calculation question based on these two topics. Okay, certain room with certain absorption coefficient, or certain revolution time value, put additional material in, this happens or that happens. Okay, so calculate this or estimate what will be happening if we do this or that to that particular room. Okay, I think I don't want to repeat this. Since you have the slide, you can read this by yourself. Okay, if we use balanced tube, okay, we can calculate what will be the absorption coefficient based on sound that is directed 90 degrees towards the surface of that particular material. So what is an impedance tube? Impedance tube is basically a tube, okay, whereby you have speaker at one end that is generating sound, and the sound will travel within this tube. Okay, so what's the purpose of this tube? We want to ensure that the sound is along the same line. Okay, so basically we want everything to be constant there, and then the sound will hit the material at one end of the tube. Okay, so when the sound hits the material, part of it will be reflected, part of it will be absorbed. So based on the ratio between absorbed and reflected sound, we can calculate what will be the amount of absorption for this particular material. Okay, so using impedance tube, we have two approaches. One is to calculate it using standard wave equation or transfer function method. Okay, both of these approach are standard approach. They are available in standard ISO documents. Okay, so initially people are not using those two equations. Okay, they are using standard wave equation in the form of Kunz tube measurement. Okay, so in a Kunz tube, so what we have here, we have a speaker, okay, that is generating the sound, and the sound will propagate within this tube. Okay, and since the sound is trapped within this tube, it will goes back and forth, and so on. Okay, so the material is here. So some of the sound energy will be absorbed by this material. Okay, fine. So the sound is moving in a plane wave motion, okay, due to the tube being used here. Alright, of course, the smaller tube will be effective to will be more effective in testing higher frequency compared to larger tube. Okay, so we will be generating a tone sound using the speaker, the kind of sound. Okay, and this sound will hit the sample and reflect it back, and at a certain instant we have what we call a standing wave. Okay, so basically we have a region whereby the amplitude is maximum and minimum. Okay, so we'll be moving this probe tube. Okay, so at the end of the probe tube we have a microphone, and along this tube we have opening here, so the sound will go inside the tube and can be measured using this microphone. So we'll be measuring the region of high and low sound energy. Okay, so that's the idea. Okay, so from this high and low sound energy, we can calculate what will be the absorption of this material. Okay, so this is basically a standing wave approach. Alright, so if you want to see how standing wave looks like, this is not directly related to sound. It's more like a standing wave in vibration, but you can relate this closely to sound. Okay, it's basically the same thing. You can have standing wave in vibration as well as standing wave in sound.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, yeah, let's go a little higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect destructively interfere with the incoming waves right here, and that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, this is a node, and the middle's a node. So we have 3 nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go.
Okay, so that's basically what we meant by standing wave. The same applies to sound wave as well. So we have a region whereby the amplitude is highest and amplitude lowest as well. Okay, so in a cone tube, if we have a perfectly reflective material, basically it reflects all the sound, we will have a total cancellation at 1/4 wavelength from the end. Okay, so at the end here we have our test sample. If this test sample happens to be something that doesn't absorb sound at all, it reflects all the sound, so we know that the minimum location should be at 1/4 wavelength from the end. Okay, or D1 should be equal to 1/4 of the frequency. The frequency of sound is controlled. Okay, we are sending a tone sound, which we know frequency, which means we can also calculate what will be the wavelength of this frequency. Okay, if this value of D1 happens to be 1/4 of that wavelength of this particular sound that we send within the tube, we know our test sample is actually reflecting all the sound. Okay, right? However, if we have a perfectly absorptive material, then we know that there will be no reflection at all. Okay, the sound will go through. There will be no region of maximum and minimum. Okay, why is that? Because there's no sound being reflected back within the tube. Okay, so of course there's no such thing as perfectly reflective and also perfectly absorptive material. Everything will be in between. Okay, so by knowing this minimum and maximum region, we can calculate what will be the absorption coefficient of this test material. Okay, so the absorption coefficient is given by this equation. So AN, or absorption coefficient for this particular material, is equal to 4 P max, or the maximum pressure over minimum pressure, divided by 1 plus P max over P min squared. Okay, so the maximum and minimum pressure is known by moving this carriage along the line, okay, to determine where our sound pressure is minimum and where it is maximum. Okay, we can also calculate how much is the acoustic impedance, okay, using D1 and D2 as well. Okay, so I don't want to move into this in much detail, but it is doable using this approach. Normally, nowadays we don't use standing wave approach. We use transfer function approach because it is much more simpler in terms of construction of the tube itself. In this case, we just have one speaker, and instead of having one microphone, we have two microphones. So we have incident sound and reflected sound towards our sample at one of the end of this tube. Okay, so in this case, the amount of reflected sound wave will depend on the absorption of the sample. Okay, and we know the diameter of the tube will dictate what will be the upper limit and lower limit of our frequency. Okay, so the wavelength of the highest frequency will be governed by this equation. Okay, which is equals to F upper should be less than 0.58 times C over D. D is our tube diameter. Okay, and we also have to ensure that the phase difference between the incident and reflected wave should be at least half of a wavelength. So our upper frequency that we send to our speaker should be also less than 0.45 C over S. Okay, S is basically the distance between our microphone that we use to measure the sound. Okay, so we need to ensure that the wavelength is long enough such that we can measure the difference in sound pressure. And the lower frequency is governed by this equation, which is F lower should be larger than 0.05 C over S. Okay, again, S is our distance between the microphone. So we will control the effective frequency based on the diameter as well as the spacing between the microphone. Okay, so the idea is simple. We generate sound to the speaker, so there will be incident and reflected sound. Our microphone will measure this incident and reflected sound. Okay, so we have sound pressure level for mic 1 and mic 2. Okay, and then what we do, we transform this sound signal into a frequency domain, and we calculate what will be the transfer function H12 based on the cross spectrum between mic 1 and mic 2, and then we calculate what will be the reflection factor and also the absorption coefficient of this material. Okay, all of these equations are dictated by ISO document as well. Alright, so this is example of impedance tube. So this is the Mercedes of impedance tube, I would say, from B&K. One of this set will cost you about 400,000 ringgit. Okay, probably now it's much more expensive. A cheaper version might look something like this, okay, or like this. Bear in mind, you can make this yourself actually. Okay, if you know your parameters and what to do in terms of controlling the accuracy of the device. Okay, so the one in Brazil and US here are DIY version of the impedance tube. Okay, it will give you about similar result. You need to ensure that your tube is acoustically closed tube, which means the tube thickness needs to be thick enough so that it will not vibrate. Okay, if the tube wall is vibrating, that means you are losing some portion of the sound energy. So the absorption that you measure is not the true absorption. Okay, it's absorption plus losses due to tube wall vibration as well. Okay, which is not acceptable. Okay, so that's how we control the accuracy of the device. Prevent all leaks as much as possible, and then ensure that there's no vibration from the tube wall. Okay. Alright, so we know if we have a wall or sound barrier, we have incident wall being reflected. Okay, some portion of this sound energy will be absorbed by the wall. Okay, and some of them will be left transmitted to the other side of this wall. Okay, of course we want to have a zero as much as possible, physically possible to do that. Okay, so we have incident sound, we have absorbed sound, and we have transmitted sound. So there are relation between these three parameters. Okay, depending on our sound barrier parameters or the absorber that we put inside our sound barrier. Okay, so if we want to measure how much sound is being insulated by our wall, okay, we can calculate what will be the magnitude of sound insulation. Okay, so sound insulation is given by 10 log 10 W1 over W2. W1 is sound energy incident to the wall, W2 is sound energy transmitted after the wall. Okay, so if we have 100% sound energy, W1 equals to 100%, and then we transmit only 10% of energy, W2. So in this case, we have 90% reduction in terms of sound energy. The insulation of this wall is equals to 10 dB. Okay, if we have 100% sound energy and only 1% transmitted sound energy, the insulation of this wall through this equation will be equals to 30 dB. Okay, if we have 100% sound incident and only 0.1% sound energy, the sound insulation is equals to 30 dB. And if we have 100% sound incident and only 0.01 sound energy being transmitted, we have 99.99% reduction in sound energy, which equivalent to 40 dB sound insulation. Okay, so the performance of insulation is largely determined by the mass of the wall. Okay, of course the wall cannot be porous, okay, but it needs to be heavy as well to prevent sound from passing through it. Okay, so sound insulation requirement depends on the purpose of the room as well. Okay, and it depends on standards. Okay, so for example, in this case I'm referring to England standard. So wall needs to have certain sound insulation properties, floor needs to have certain sound insulation properties, and so on. Okay, in Malaysia, I'm not sure whether we have this kind of sound insulation properties. Why is that? Normally our houses are constructed in such a way that we have windows that opens like almost 20 hours per day. Okay, we have opening in our houses a lot. Okay, in these countries, these temperate countries, temperate climate countries, normally their houses are have no, they have windows, but they don't open their windows because they want to trap all the warm air inside, or they don't want any cool air from entering their house. So everything is closed. So in these instances, the sound transmitted by wall, floor, and so on tends to be more critical compared to us. In our case, even airborne noise is much higher compared to this structure-borne noise or sound being transmitted by wall or floor. Okay, so that's the reason why we don't have this kind of standard, I think. Okay, so if we have a wall, we have incident sound energy that will be reflected, transmitted, and so absorbed. So based on this, we can calculate sound transmitted coefficient, which is equal to incident transmitted sound energy over incident sound energy, incident sound intensity. Sorry, okay, transmitted sound intensity divided by incident sound intensity, and then we can also calculate what will be the sound reduction index R, which is equal to 10 log 10, 1 over this sound transmission coefficient. Okay, for a whole, or basically window that's open, the sound transmission coefficient will be equal to 1. Okay, why is that? Because there's no reflected sound, so all transmitted sound will be equals to the incident sound. Okay, so sound transmission coefficient will be equals to 1, or R equals to 0. Okay, of course, for practical wall with multi materials, our sound transmission coefficient will be a combination of this material as well as their surface area. Okay, so the average sound transmission coefficient will be equal to the sound transmission coefficient for each material times the surface area for each material, sum of them divided by the sum of all the surface area of the material within the wall. Okay, so the average sound reduction index will be 10 log 10 over 1 over the average sound transmission coefficient. Okay. All right. I think I want to stop here. Any question, guys?
No question there.
No question. Okay. For this topic, I know there's a lot of equation and so on. I told it so much because in final exam normally I give all the equation. It's just a matter which one to use. Okay, that you need to worry about. And the concept is not so difficult. Okay, I believe if you try to do the example, okay, try to understand the underlying principle behind the example, you can start to see where this equation can be used for each particular problem. Okay. If there's no question, I'm gonna stop the class here. Okay, I think I've overly worked some of you for the first class after holiday. Okay, with lots of equation. All right. If there's no other question, I think for the video assignment, most of you have submitted your video. Okay, it's quite fun watching it, and some of you still having some problem. Okay, so you need to submit them as soon as possible. Mr. Khairul Alif, I think you need to give me your link again. It broke down somewhere, probably you are missing some character in the link. I can't open the link. For the rest, I can open your link. Some of you did send me the link through WhatsApp and double confirm whether I can open it or not. I can open all of them. Okay, even though you put it inside your comment. It might not be the right link, but somehow I can extract it from the comment. Anyway, okay, so here we have only 1, 2, 3, 4, 5, 6 people who have not submitted yet. Mr. Diva, Mr. Nofidaus, Mr. Ragib, Mr. Shurin, Mr. Khairul Alif. Of course, you need to resubmit the link, and Mr. Muhammad Rahul. Okay. For the rest, no problem at all. I can open your link. Okay. So I'll stop the class here. See you again on Wednesday. Thank you very much. Yep. For assignment 3, if I'm not mistaken, it's 2 weeks after our class start. Basically 2 weeks from today. Is it okay? Okay. All right. Thanks again. See you again on Wednesday.